alternative transport.
The WarpLink system has the capability to not only reduce trade emissions, but improve the speed of delivery and cater for future trade volume. Take London. We could link the 3,500 mile crossing across the Atlantic to New York that takes a ship approximately 7 days to complete. We can do it in 4.5 hours. Let's take the inland transport from New York to Los Angeles, a 2,800 mile journey that by truck takes 2 days approximately. We can do it in just under 3.5 hours. And what if we connected two giants? Los Angeles to Shanghai, a 6,500 mile crossing over the Pacific Ocean. By boat, that would take 17 days. We could do it in 8.5 hours. Let's show you how. WarpLink is a network of evacuated tubes running from the UK's major container shipping ports to central distribution locations. Evacuated tube technology, or ETT, allows pods carrying containers full of goods to travel between hubs at speeds of up to 760 miles per hour. Extremely low pressures are maintained within the steel network, effectively making the air resistance negligible. This allows objects within to travel at much faster speeds. Initially, WarpLink intends to utilise this technology within the UK, with expansion plans being made for the future. WarpLink is a highly regarded dynamic company with a team of efficient, multidisciplinary engineers who are focused on developing and enhancing innovative solutions to problems through pioneering design processes. WarpLink is a leader in technological advancement with experience and knowledge in a range of fields. To ensure WarpLink maintains its competitive edge, it invests heavily in its people and equipment to guarantee a high standard of competency. Whilst designing and implementing, WarpLink always considers sustainability and corporate social responsibility. Our team consists of 7 multidisciplinary engineers, including 3 civil engineers, 2 civil and coastal engineers, 2 mechanical engineers, with over 13 years of combined industrial experience. Let's introduce the WarpLink team. Matthew Franklin, our project director. James Mayfield, our project coordinator. Lydia Hunt, our Civil Works Director. Ryan Sorby, our Electrical Works Director. Jason Rolfe, our Port Integration and Traffic Director. Jasmine Toombs, our Structural Director. Rhys Parsons, our Mechanical Works Director. WarpLink follows a flexible company matrix with Matthew Franklin, our Project Director, at the top, and communication flowing freely through the team. Our vision: to revolutionise global transportation of both people and cargo, utilising renewable energy, linking communities and countries across land and water at sonic speeds. WarpLink intends to design a sonic speed trade network in the UK with a vision of expansion in the future. To understand where to locate the network, key ports throughout the UK were identified with central distribution hubs located centrally. The first of the ports for consideration was Felixstowe. Felixstowe is currently the largest serving port in the UK and will be the primary focus of the initial phase of WarpLink. London Gateway, poised to be the largest port in the UK through a number of ongoing expansions, and is a key connection to the south. Southampton already has a large container infrastructure and is a welcome addition to WarpLink in terms of reducing road congestion and pollution. Bristol has development plans to increase its container capacity and has excellent connections to the southwest of England. Liverpool is one of the largest serving container ports in the north and will serve as a valuable connection to this region. Forth is currently the largest serving port in terms of capacity to Scotland. Tees and Hartlepool is a hub of commerce to the northeast and is the final port considered for the UK infrastructure. The two distribution centres that link the ports are located in Milton Keynes and Oldham in the south and north respectively. These were chosen as they were key areas for the transportation of goods. The initial phase and the key route studied is the route between Felixstowe and Milton Keynes, the southern distribution centre. This route measures a total distance of 138.8 kilometres. The second phase connects the two distribution centres of Oldham and Milton Keynes. The final 6 phases will connect the ports to the distribution centres and will be discussed in more detail later in the presentation. As ships arrive at the port, containers are offloaded by ship-to-shore cranes, where automated guided vehicles bring containers into the port stacking areas. Depending on the priority of the container, it is brought into the loading-unloading warehouse designed to integrate into existing port automation systems, and the container is loaded by an automatic stacking crane to be sent to the final destination. A potential bottleneck to the system would be the efficiency of the loading and unloading system at the ports and national distribution centres. To counteract this, a suitable mechanical system was put in place. Depressurization of the pod is a fast process that can be achieved in under 1 minute by changing the pressure level from 100 pascals up to 100,000 pascals. Through the use of conveyors, the pods can be swiftly moved along the line and its doors opened. Containers can be efficiently removed with the side loaders before the pod moves forward and lifted to the other side. As each pod is required to face one way, a rotating gantry is utilised to place the pod in one swift movement. The whole process is synchronised, allowing for a highly efficient system, reducing any risk of bottlenecks. The idea of such high-speed travel aims to make the use of low-pressure environments, through which the capsule will experience lower aerodynamic drag than at standard atmospheric conditions. Air from the tube is collected and compressed using an axial compressor at the front of the capsule. Approximately 60% of this air is then directed to the rear of the capsule to a diverging nozzle, the thrust from which is enough to overcome the drag force and frictional forces in the support bearings. The residual air is stored in pressure vessels in the capsule walls, where it is gradually fed to the air bearings on which the capsule is supported. To avoid a situation where too much air builds up at the front of the capsule, a system is designed within the Karowitz limit. So, although we get the Bernoulli effect where the air velocity increases in the narrow regions between the capsule and the tube, the flow does not become choked. The WarpLink capsule is propelled using linear induction motor technology. The two parts of a conventional induction motor uses a rotating magnetic field in the stator, which links with the rotor magnetic field, producing rotational motion. The linear motor has a stator rolled out in a line, so the WarpLink tube floor will form the stator. Windings on the capsule will form the motor stator. This arrangement will cause the capsule to accelerate at 2.5 meters per second to over 700 miles per hour. Stanchions are positioned at 30-metre centres and will consist of 2 tubes positioned on a single column. The height of the stanchions will allow a minimum clearance of 6 metres, as directed by Highways England. The tubes will have a diameter of 6 metres and a thickness of 30 millimetres. The national distribution centres connect the ports to each other and also provides a central location for distribution. The loading and unloading warehouses are identical at every location, which allows for simple modular design. The site has a dedicated maintenance warehouse where minor faults and servicing of the containers and pods can occur. It includes 2 dedicated loading and unloading areas where HGVs can drop off and collect containers. The office located at the National Distribution Centre will act as a central core to all of WarpLink's operations. Remotely controlled systems spanning the entire network will be centrally monitored from this single office. The office is open plan and will accommodate WarpLink employees as well as allowing space for haulage firms. This office has been designed to maximise the thermal mass of the structure, adoption of renewable energies, and optimising the use of natural light through its extensive curtain glazing and vast atrium. The user interface can be loaded from any handheld device. The interface allows employees and customers to estimate transportation times and the greenest option between HGVs and the WarpLink system, as well as book journeys, track containers, and find containers in the stacks. Additionally, it is possible to track the delivery on a Google Earth map with live updates and estimations. The UK WarpLink network is to be divided into 8 phases, the first phase being the initial implementation of this new technology, phase 2 connecting the south of the country to the north, and phases 3 to 8 potentially occurring concurrently, connecting the remaining identified ports within the UK. The design and development of phase 1 is to commence in July 2016 and is envisaged to run through to July 2017. The construction of phase 1 is proposed over a 4-year duration. The development of the NDC will commence immediately and will then be utilised as the project's main office. The route will be constructed over the duration of 4 years and the port hub scheduled to finish alongside the completion of the route, resulting in a minimum disruption to the port's operation. The design of phase 2 is due to be completed to allow for the commencement of works on completion of phase 1. Phases 3 through 8 will follow. WarpLink's strengths are centralised around the fact they are a diverse range of highly motivated engineers with a combined experience of 13 years. WarpLink have also developed comprehensive management procedures, making them efficient and organised. The primary weakness of the WarpLink team is that the concept of the design is relatively new, thus there is no construction and little design knowledge of the proposal available. In contrast, the fact that the concept is relatively new is also likely to work in WarpLink's favour, as it provides WarpLink with the opportunity to become a market leader in the UK, with the possible expansion to Europe. The threats associated with this study are likely to be a combined result of the new technology causing unanticipated setbacks and restrictions from indirect stakeholders such as the government and locals. Users are primarily the shipping companies and port authorities. Businesses include energy providers and current freight transportation companies. The social and local stakeholders comprise of schools, universities, landowners and local residents. The environmental stakeholders identified consist of Natural England, English Heritage and the Environmental Agency. The government teams impacted are typically county councils and national government, and the stakeholders identified by the other category are principally utility providers. As with any projects, there are potential risks that can occur. These include, but not exclusively, loss of work through various means, difficulties in relationships between team members, disagreements of design concepts, loss of profit at project's completion stage, delayed delivery of completed construction, limited access to and around construction sites, and most significantly, public disagreement with the proposed concept. Let's take a look at the figures behind WarpLink. The first phase between Felixstowe and Milton Keynes is expected to cost approximately £5.8 billion. With the route being the largest cost, construction and contingency costs have also been included. The entire UK project is expected to cost approximately £51.25 billion. These costs have been identified using the costs established from Phase 1 of the project. It is expected that construction will last 15 years. Once fully operational, a yearly income of £779 million is predicted. This allows WarpLink to break even after 79 years. The initial network expansions would link the UK to nearby European countries. Once Europe is connected, the company should focus on intercontinental links. WarpLink also has the potential to expand into passenger transport. With cross-continental links complete, large shipping vessels can be decommissioned and the era of WarpLink can commence. With the UK moving more than 151 billion tonnes of cargo by road every year, switching to WarpLink will ease an enormous amount of congestion, as well as reducing pollution. The WarpLink system emits a whole kilogram less of CO2 per mile than a HGV. In the last year, government statistics estimate HGVs have travelled 16 billion miles within the UK. This is 16 billion kilograms of unnecessary CO2 in the atmosphere. The WarpLink system is not only quicker and better for the environment, it is also cheaper than current transport proposals. The UK government has approved the construction of the High Speed 2 rail project, which they have estimated will cost £80 billion. The High Speed 2 network will cost £170 million per mile. We predict that the WarpLink network will cost only £67 million per mile, whilst being greener, faster, and the future of transportation.